Uh, so today is last lecture for this class. Okay. Next week we have programming exam and the final exam. Programming exam is on Tuesday. Final exam is on Wednesday. Okay. So as I said, okay, we don't have time to cover min-max flow, which is also a very important topic. But I think NP complete is even more important topic. Okay, so I decided to drop the min-max flow and to cover this one instead. Okay. And for min-max flow, I gave you the handout. It's unfortunate, like we didn't have time to cover that, but you are welcome to study the handout and get a little bit knowledge about that topic too. Okay, and also okay, just like any. Just like previous setting, okay, I will always assign the homework like every 2 weeks. So last week, okay, the Floyd-Marshall algorithm, as well as today, okay, the NP complete, I will assign the last homework, which will consider you are, I mean, you need to, do the exam next week. So this homework will due like after the final, like a week after the final, which is like, I think it's Friday of next week. Okay, so you should have plenty of time for that. Okay, but of course there are two things. Okay, I want to assign this homework to you. Okay, now because first, I mean, the homework could be a clue to your final exam. Okay, second, you get one more chance to improve your grade, okay? Because for the homework, we are going to select like the better homework out of this all the homeworks that you submitted. So if you feel like you already earned enough credit for the homework, you don't have to submit this one, of course. But if you think like you have a chance to improve your grade through this homework, of course, like it will be a good opportunity for you to submit. Okay? So, and also, I'm not in a good condition today. Okay, I feel dizzy. Okay, starting last night. I don't know why, but I heard that, I mean, some other people have similar symptoms. It may be the effect of the magnetic field. I don't know. 他们不是说地磁吗？最近这几天地磁比较严重，说对人也会有影响。I'm not sure if that's because of that, or it's just because I'm going to get a cold or something. Yeah, but so today I think it's better for me to sit down and talk about this NP completeness. Okay. So yeah. So what is NP complete? Okay. So in this semester, we discussed like various problems, okay, and the algorithm, associated algorithm to solve those problems, okay? And we consider those algorithms as our tool, okay? So, of course, that's the primary reason you enroll this class, okay? This class is called Introduction to Algorithm, anyway, okay? But we also need to be able to find a boundary of the problem that we are able to solve, okay? It's not like you can solve everything, okay? So we need to prove that a problem is extremely hard, okay? How hard is the problem, okay? This is the main thing of this chapter, okay? If we can prove a problem is very hard, then we probably don't need to waste the time to solve that problem, okay? It's like this. If your boss tell you to do one job, okay, one way to answer that request is that you can just, try your best to finish the job and tell your boss, okay, yeah, it's done. A bad way would be, okay, you just tell your boss, I cannot do it. I mean, because the job is difficult. It's not good enough, right? Your boss will not listen to that, right? 我的意思说，如果有一天你老板跟你讲，叫你做一件事哦，就是你在外面工作，你老板叫你做一件事，你如果跟他讲说，一个当然最简单，你就把它做掉了。那做掉，那当然就是一个最好的回应。但是你如果不能做，你觉得这个问题很难，你就跟老板讲说，我没办法做，这个问题太难了。老板不会买单的 ，OK？ Your boss will not buy it, OK？ But if you can prove the job your boss, assigned to you is unreasonable in the sense that not only you cannot do it, okay? It's like all the smart people in the world cannot do it. 就说你可以证明给你老板听说，不是只是我不能做哦，是所有世界上聪明的人都不能做。Then your boss cannot say anything, right? Even if he replace you with another guy, 就算他把你 fire 掉，然后去找另外一个人，还是不能做嘛，对不对？所以这才是一个 that's the right answer, right? That's what I call a right answer. Okay, so that's the purpose of this lecture. Okay, the boundary. What is the upper bound, okay, for the problem that we can deal with, okay? So NP-complete problems are hard, as we will discuss later, okay? NP-complete problems are difficult. So we will go over a few of them, okay? And we will also show how we can prove a new problem is NP complete. This is also very important, okay? Actually, one of the first few papers that I published, okay, I published that paper in Algomisca, okay? That's like a journal dedicated to algorithm design, okay? And the paper I published there, okay, the reason I could get the paper accepted is because there's a part of the proof, there's a proof that I'm using the technique I learned from this lecture, okay? 就说在 paper 里面，我证明了一件事情，证明那个事情的那个技巧，其实是用这里面这一章里面教的技巧哦。对，其实蛮好玩的哦，其实蛮好，这个技巧其实是蛮重要的。Okay. So, before we start, let's try to classify the problems into a few categories. Okay. So, this set is called NP. Okay. And we have another set of problems called NP hard. Okay. And the P, so what is NP, what is P? NP complete is like the intersection of NP hard and NP. Okay, it's here. Okay. But what is, so you don't know NP, you don't know P, I mean, what does that mean? Okay, what is NP hard? P is the problems that exist a polynomial solution. These are the set of problems. 这边都是问题的集合哦，问题的集合。那 through this course, all the problems that we are discussing, or we have discussed previously, belong to this category, polynomial. Okay, we talk about a few bad implementation of some problems in our class. The complexity is exponential, right? Okay, but still those problems exist polynomial solutions. Okay, so if a problem exists a polynomial solution, okay, it belongs to P. It does not necessarily mean all the problem that solve all the solution that solve that problem are polynomial. No. I mean you could have a very stupid algorithm, okay, that solve a very simple question in exponential time, right? So that doesn't change the fact that that simple problem belongs to P, okay? So it's a set of problems that can be solved in polynomial time. Some examples such as sorting, such as shortest path, such as a minimum spanning tree. Okay, all those problems they belong to P. So what is NP? NP is the set of problems that can be first solved in non-deterministic polynomial time. What does that mean? Consider you are able to execute something, a machine, okay, that has an infinite number of CPUs. 就你可以假设说，你有一个机器可以无穷无尽的平行计算，它可以一次平行计算随便多少个数目字的这个事情。If you have such a machine, and you are able to solve that problem in polynomial time, then that problem is considered to be NP. OK， 就是你如果说有无穷多个，我举个例子来讲，你想要证明一个，譬如随便讲，我举个例子来讲，那个 LCS longest common subsequence，longest common sequence，OK， 我们那个时候讲的那个题目嘛，给2个 sequence， 我们要证明它。记不记得有一个 solution 是怎样？我们对每一个那个子序列，我们去看另外一个那个 sequence 有没有包含它就好了，对不对？那个检验很快，对不对？但是你如果想想看，我们如果说要看所有的子序列，那是不是有exponential 的子序列，对不对？有指数这么多的子序列，那假使我们平行的把这些检验的演算法一起跑，那你整体的时间是 polynomial， 对不对？只不过我们可能没有这样的 CPU 啦。We just may not have such a CPU that can run the algorithm infinite number of threads in parallel. Okay, that's not likely. But theoretically, that's theoretically speaking. Okay, so we call such a situation as non-deterministic. If you are interested in non-deterministic, what non-deterministic is, okay, well, I occasionally offer like a theory of computation. If enough students are interested, I mean, I can offer that course again. Okay, in that course we'll discuss many different computational model, and non-deterministic is an interesting nature for many machine model. Okay, but anyway, okay, that's the first one. The second one is that NP means we can verify, okay, in polynomial time. So for all these different threads, infinite number of threads, now all these threads will terminate in polynomial time. Okay, in polynomial time. So we need to satisfy these two conditions in order for a problem to belong to NP. So think about this. When you define NP like that, the polynomial, the problem in P is actually a special case in NP, right? Because obviously, the P will be an NP problem that requires only one thread, right? So P could be considered a special case of NP. So that's why P is a subset of NP. Okay, so now we know what P is, what NP is. Then what is NP hard? NP hard is a set of problems that are as hard as or even harder than the hardest problem in NP. But how do we define which problem is difficult, which problem is hard? We need a formal definition of that. Okay, I will talk about that later. Okay, that's also a key concept of this chapter. And because of that concept, we are able to construct a special subset, which is a NP hard, the intersection of NP hard and NP. We call that intersection as NP complete. It contains a set of problems that are both NP and NP hard. And the problems in the NP hard, NP complete, okay, we can prove they are equally difficult. Okay, equally difficult. I will show you how we can prove that. Again, it's about, how we can prove a problem is hard. For example, if you can prove A is harder than B, and B is harder than A, I probably should use harder. I should use like A is at least harder than B, or B and B is at least harder than A. Then you can say A, B are roughly equal difficult, right? 你说两个问题 ，A 至少比 B 困难，然后你又知道说 B 至少比 A 困难，那你是不是这两个问题就差不多困难？对不对？对，所以这就是 Once we have a technique to prove a problem is at least harder than the other, we are able to construct a subset called NP complete. In this subset, every problem are, as hard as the other problems. Okay. So now we have explained all the terminologies here. Okay. To be honest, do you consider all the problems have been discussed here? All the computational problems, will be covered by this couple sets. Is it? 是不是这里面就包含所有可以被计算的问题 ？Yes or no？ 你们觉得？没有人有意见？多少人觉得是？这里面已经包含所有的可以计算的问题。多少人觉得是？多少人觉得不是？有几个同学对不是举手啊？那其他都没有举手，也不知道说是怎么样想。结论是不是哦？不是。There are problems that are even harder, in the sense that we can prove there's no algorithm to solve them. 有更困难的计算的问题，我们可以证明，没有演算法可以解它们。我们可以证明这件事。但是那些问题当然不属于这里面的了。好。So a problem is NP hard if you can do the following. First, show how to verify a solution. Any solution. In polynomial time. Because we have to, at least at first, make sure the problem is NP, right? So we first verify a solution. If you are given a solution, you verify the time for the verification. Should be done. This verification should be done in polynomial time. And also, the second job is that you need to show the problem is NP hard. How? By showing this problem is at least as hard as a non-NP complete problem. Now we are talking finally at a time to talk about how we can prove a problem A, is two problems. Okay, A is at least more difficult than B, something like that. Okay, so you can take a current known NP complete problem. We call that problem A. Okay, and our problem, suppose our problem is X. You need to show that A is polynomial. X is polynomial reducible to A. Okay, this terminology is called reducible. Reducible. Okay, you can reduce X to A. This P means this reduction process needs to be done in polynomial time. Okay. So what exactly is this? It's like this. I will explain repeatedly, okay, because this chapter is different from the previous chapters because it's a conceptual proof, okay, and the proving technique is very interesting. This reduction proving technique is interesting, and if you don't get it the first time, that's perfectly fine. So that's why I'm going to talk about this like repeatedly. Okay. So it's like this. Okay. We know A is hard, right? A is difficult, right? Think about this. If you are able to convert A's solution, or put it another way, you are able to transform problem A into an instance of problem X. Okay, and if in polynomial time,就如果说你可以把 A 这个问题随便给 A 一个问题。你可以把这个随便给了一个 A 问题，可以有系统的把它用那个 polynomial time 变成 X 的一个问题。变过去了以后呢，原来 A 的问题有解 ，if and only if 你变过去的那个 X 问题有解。然后呢 ，and then if there exists a polynomial solution for X, then somehow you can convert that solution back to the solution for A. Again in polynomial time. 就如果说我们有这样子的转换，那然后 X 又可以。假使我没有说存在，我说假使 X 存在一个 polynomial solution， 那可以把那个问题解掉，你解掉你就有 solution 了嘛，对不对 ？And then if that solution also take polynomial time to be, transformed back to the original problem in A。如果你那个 X 的 solution 可以在 polynomial time 再把它转换成原来那个 A 的问题的解。Then think about this. Previously, we say A is hard, right? A is NP complete in the sense that, it's so far there's nobody is able to find a polynomial solution for A, right? Now, you translate that problem to X, and assuming there's a solution for X, you solve that problem in X, and then you convert the solution of X back to A solution. Then through this whole process, you find a polynomial time solution for A, right? So we have a contradiction, right? We have a contradiction. Well, so this means what? This means if X exists a polynomial solution, A exists a polynomial solution, right? Right? Or I could say that X is at least as hard as A, right? So, and also, because A is NP complete, because we particularly choose a problem from NP complete set. So, not only we prove that if X has a polynomial solution, A can be solved in polynomial. Because, I mean, in the NP complete, this I just previously told you, this NP complete is a set of problems that are equally hard, right? What do we mean by equally hard? That means, you know, every problem can be reduced to the other, right? So, in other words, okay, because A, you know, any NP problem, problem can be reduced to, I mean, A can be reduced to any NP problem in polynomial time. So in other words, so if you prove that X has a polynomial solution, not only you prove A has a polynomial solution, you actually prove any NP problem has polynomial solution. Okay? So, in other words, you prove that P, the set P equal to the set NP. Is it possible? Nobody has proven that yet. Okay? I'm not saying it's 100% impossible. I'm not saying it's possible. Okay? This is one of the most difficult problems in computer science. Okay? If you can solve it, you win the Turing Award immediately. Okay? So, but anyway, I just want to tell you, this is the technique. This reduction is an important technique. Okay, to show one problem is at least as hard as some other problem. And that's the theme of this this chapter. Okay. So to prove a problem is NP complete, first you need to show the problem is NP. In other words, you need to verify. You need to be able to verify a solution is indeed a solution in this problem in polynomial time. Second, you need to show the problem is at least as hard as a given NP complete problem or NP hard problem. Okay, so that's it. These two steps. So because NP complete is the set of hardest problem in NP with these important properties. If any one NP complete problem can be solved in polynomial time, then every NP complete problem can be solved in polynomial time. Okay. And actually, okay, if that's the case, every problem in NP can be solved in polynomial time because P is a subset of NP. So this, I mean, you know, basically means the set P equal to the set NP. Okay, another possible contribution that you can make is that if you can prove any single NP hard problem has an exponential lower bound, any of them, if you can prove any of this NP hard problem has exponential lower bound, then every NP hard problem, okay, including the problems in NP complete, is exponential. So it's like this. Okay, let's use this reduction. Okay, as I said, like this reduction or this smaller equal sign is at least as hard as, right? Okay, but you need to read backward. Okay, you know, a smaller or equal x means x is at least as hard as a, right? Okay, so. So if what I just told you is like, if A exists a polynomial time, I mean, if we can prove A has a polynomial lower bound, any algorithm to solve A must has a complexity, you know, above like in polynomial time. Then, because x is as hard as A, right? So x must also have, like, if x has any solution, x solution must be exponential too, right? If A has an exponential lower, if A has exponential lower bound, then x, I mean, we can say x will have at least exponential lower bound too. So that's what we meant here in this point. This is also important. This tells us, this guarantee P and NP are not the same. So it's an interesting thing, okay? No matter you can prove P equal to NP, or if you can prove P does not equal to NP, either case, you win the Turing Award. Okay? The smartest people in the world, okay, those computer scientists, like mathematicians out there, they couldn't find a solution. They couldn't find a proof. And this is about any problem in NP complete this set. How many problems are there? There are thousands of such problems. Okay, so that's why I told you, like, if a boss tells you, okay, to get this job done, and you can, if you are able to prove, okay, this problem is difficult. I mean, if this problem, for example, is NP complete, then you can tell your boss, you know, if I can solve this problem, okay, basically I don't need to work for you, okay, I can, you know, I can become rich, you know, instantly, okay, I can win the Turing Award and, you know, retire, you know, in a, you know, and lie on the beach and drink your, you know, pina colada, yeah. So, anyway, so solve traveling salesman, salesperson problem. Traveling salesperson problem. This is known. By the way, traveling salesperson problem is known to be one of the NP complete problem. Okay, what is traveling salesman problem? Traveling salesman problem means that you are given any graph, given a you know graph, right? Okay, you are given any graph, and you need to design an algorithm that finds a path, okay, that, visit every node exactly once. Okay, and you need to find, shortest path that does that. Okay, so if you can solve this problem in n to the power of 100, that's a lot of a big order, right? But it doesn't matter. It is still polynomial, right? It is still polynomial. You prove that P equal to NP, retire, rich, and famous. Okay, you can. So this is like something. It is very difficult. Okay, traveling salesperson problem is also difficult. Okay, by the way. So come back to this reduction, because this is the key of this chapter. So let's spend some time to look at it. This is we are talking about the process of this reduction. The problem we don't know how to solve is A. You just remember, if you want to prove a problem is NP complete, then you need to handpick one problem, okay, from NP complete, and put that problem as A. Okay? But anyway, let's assume this A is a problem you don't know how to solve. And the B is the problem you know how to solve in polynomial time. Okay? And if you are able to map the instances of problem A to instances of problem B, so given a problem A, you can convert that problem to a problem in B, and then use the B algorithm to solve the problem. Oh, by the way, this conversion also has to be guaranteed in polynomial time. And once you solve that problem, you get a solution for problem B, right? And you need to be able to map that problem, that solution, back to the solution for the original problem A. And this mapping needs to also be done in polynomial time. So you see, from A, and originally, if you don't know how to solve it, you can convert it to B in polynomial time, solve this problem in polynomial time, and map the problem, map the solution back to the solution for A in polynomial time. So this cycle, well, this is not exactly cycle, this path provides a polynomial time to solve problem A, right? So that's the concept of problem reduction. Okay, and if such a process exists, we call A smaller equal PB, or we can say B is reducible to A. Okay. And that P stands for these two mappings needs to be done in polynomial time. Okay? So far so good, right? Okay, this is the case when we don't know how to solve A, and we know how to solve B, and we can sort of make use of problem B, the solution for problem B, to solve problem A if there's such a reduction, like a relationship between A and B. And you can sort of, because we are in computer science, you can sort of try to rationalize this as like there's a procedure to solve B. So you can sort of make use of a procedure, this procedure to solve the problem A, right? With these two mappings. You can use the procedure, okay, this particular procedure, okay, which is the algorithm for problem B, okay, to solve problem A. Now, okay, the same exact process can be used to show A is not in polynomials. Okay. Now, okay, we say A is a problem we don't know how to solve. Okay, and B is a problem we do know how to solve. Okay. If we are able to prove an exponential lower bound for the problem A, okay, then this process tell you otherwise, right? Tell you there's a way you can get the solution for problem A in polynomial time. But we already know, you know, there's a exponential lower bound. So what does that mean? It means what? The mapping, if the mapping are, these two mappings are valid, say if these two mappings are valid, it tells you that the algorithm for B cannot be in polynomial time, right? If it's in polynomial time, then this lower bound, this exponential lower bound, is broken, right? It's broken. So that's exactly, okay. If A smaller or equal to B, okay, and you know, if A has an exponential lower bound, okay, then we can show we sort of can imply there's no polynomial solution for problem B. Okay. So that's the reduction. We are going to revisit this process, okay, repeatedly, okay, in some instances later. Okay. Let's take a 10 minutes break. Okay. When we come back, we will continue the discussion. Okay.